Hey everybody, welcome back. Today we're going to talk about gas law variables, which is section 7.3. And so this is to kind of get us primed and ready to talk about the actual gas laws in sections 7.4, 7.5, 7.6. So there's four basic properties of a gas sample. There's the volume of the gas, which we're going to be measuring in units of liters. There's the pressure of the gas. We're going to be using units of pascals, atmospheres, torrs, or millimeters mercury, and we'll talk more about those units. There's temperature, which we typically use kelvins when we're talking about gas laws. And there's the amount of gas, which is abbreviated N for moles. So with these four basic properties of a gas sample, we can relate these properties using what are called the gas laws. And what the gas laws do is they give you a way to calculate, say, if you know the volume of the gas and you know the pressure and you know the temperature, you can calculate the unknown. So with these four properties of a gas, if you know sometimes even just two of them, you can calculate one of the others. Or if you know all three, you could calculate the fourth. And so the gas laws are mathematical relationships that tell us how to relate these four properties of a gas sample. So that if we know one, two, or three of them, we could calculate one of the unknowns, one of the properties that we don't know. So before we get into kind of the calculations part and talking about the individual gas laws, we have to talk a little bit about these four properties. In particular, we're going to talk about pressure and what pressure is, and then we're going to just briefly talk about temperature. So when gas particles collide with the walls of a container, they exert pressure on that container. So pressure is the force exerted by the particles hitting the surface of the container per unit area as the gas molecules strike the surfaces around them. So pressure is the force exerted by the gas particles per unit area. So if you imagine a cube filled with gas particles, the force of those particles hitting any one of these surfaces, the force divided by the area of the surface, that's the pressure exerted. So you can imagine if there's more gas particles, you're going to get more collisions with the surface, so the pressure would be higher. Or if there's more force, because the particles are moving faster, the pressure would also be higher. Or if you compress this cube down to say half the size, the area decreases. Since that's in the denominator, the pressure would go up. So just from this slide, there's going to be a lot of relationships we talk about with like pressure and volume and like temperature. It relates right back to this equation, right? Force, we know that if we heated up this container, by heating, increasing the temperature, we'd increase the kinetic energy, which means all these particles would be moving faster. So there'd be more force from the particles, which would increase the pressure. Or if we decreased the area, we compress this gas, and gases are compressible, we'd be decreasing the area. Since this is in the denominator, it's inversely related to pressure. So if we decrease the area, we'd be increasing the pressure. So I know this seems really simple, pressure equals force over area, but if you think back to kinetic molecular theory and how changing the kinetic energy of a gas sample changes, say, the speed at which the particles are moving, changing the force component, or compressing the gas, you change the area component, you can directly see how either of those things would affect the pressure of that gas sample. When we measure pressure, we use what's called a barometer. How a barometer works is that, let me grab my pen here. How a barometer works is that the pressure from the mass of the atmosphere, right, there's the pressure of the air in the atmosphere, pushes on mercury inside a dish, which then can cause the mercury inside a tube to go up or down. So if there's more atmospheric pressure, right, it pushes the mercury higher up the tube, and we get a higher pressure measured in millimeters of mercury, how high up the tube this mercury column goes. Or if there's less pressure in the atmosphere, then the level of the mercury inside the tube drops and we get a lower pressure reading. So if you go on, you keep taking chemistry, eventually you'll take what's called physical chemistry, and a popular lab experiment in physical chemistry is to actually build your own barometer. That's one of my favorite things I did when I took BChem, because you really get to see how this works, and you get to work with liquid mercury, which is also lots of fun. Okay, so we measure pressure with the barometer. In classic old style barometers, they measure pressure by having like a small dish of mercury with an inverted tube. And then as the pressure of the atmosphere pushes on the mercury in the dish, it causes the mercury in the tube to go up or down in level, related to the atmospheric pressure. And so that's why one of the units for pressure is millimeters of mercury, because what you're physically doing is measuring on one of these barometers how high the mercury goes. Okay, so pressure has lots of units. The one we're going to be using most often in the gas laws is atmospheres, which is abbreviated ATM. So 1 atmospheres equals 760 millimeters of mercury. 1 atmosphere also equals 760 torr. 1 atmosphere is equivalent to 14.7 psi's, pounds per square inch. And 1 atmosphere is also equivalent to 101,325 pascals. So if you take physics, pressures are typically given in pascals. PSI is from the English system. Pounds per square inch. Torrs and millimeters mercury are both from the metric system. And atmospheres is what's used in gas laws. So these are all conversion factors, right? We could write 1 ATM, atmosphere equals 760 millimeters Hg. So if we were given pressure in millimeters of mercury and we needed to convert to atmospheres, we would set up a conversion factor. So let's say we were told that the pressure of a gas, 973 millimeters Hg, and we wanted to convert that to atmospheres. We'd go 973 millimeters Hg, millimeters of mercury, times our conversion factor, and we want to use this conversion factor so that millimeters of mercury cancels out and we're left with atmospheres. So we go 760 millimeters of mercury, 1 ATM. We check our units and millimeters of mercury cancel out and we're left with atmospheres. So if I do this, 973 divided by 760, I get 1.28 atmospheres. So each of these up here is a conversion factor to go from any of these units, millimeters mercury, torr, psi, or pascals, to atmospheres. Because when we start using the gas laws, we're going to want our pressures to be in atmospheres. So the pressure units used most often in medicine are millimeters of mercury. So if you work in a clinic or you will be working in a clinical setting, you may take like blood pressure or other pressure readings in millimeters of mercury. And for this class, you should be able to convert between atmospheres and millimeters of mercury, or torr, because they're the same conversion factor. They're both 760. So you should be able to do these conversions on your own. And then I'll give you these other conversion factors, PSI and pascals, if you need them on quizzes or exams. But you should know how to go from atmospheres to millimeters of mercury, or atmospheres to torrs, or the other way, torrs to atmospheres, or millimeters of mercury to atmospheres on your own without me giving you the conversion factor. Okay, for temperature units, when using the ideal gas law equation, the temperature must be in units of Kelvin. So it's a good idea now, when we start talking about the gas laws, to just get in the really good habit of converting your temperatures to Kelvin. In the ideal gas law, it's absolutely essential. If you don't convert your temperatures to units of Kelvin when you start using the ideal gas law to solve gas law problems, you'll get the wrong answer. So I suggest you just get in the good habit of converting your temperatures to Kelvin. And so most often you're going to be given your temperature in degrees Celsius because that's what we measure in the lab with our lab thermometers. And to convert it to Kelvin, you add 273.15. If you're given your temperature in Fahrenheit, convert it to Celsius. And then from Celsius, you can convert it to Kelvin using 273.15. So again, when we get to the ideal gas law, your temperatures must be in kelvins when we're using the ideal gas law equation. For the other gas laws, it doesn't necessarily have to be in Kelvin, but I found that if students don't remember to start converting to Kelvin early on, then when we get to the ideal gas law equation, they forget there, and then you end up with the wrong answer. So just save yourself some frustration later by getting in the good habit of converting to Kelvin early on so you don't forget to do it later. Okay, so we're now ready to start talking about the different gas laws. The first one we're going to talk about next time is Boyle's law. I'll see you then. Thanks.